then what do we do, and what do we do once we get them?
Panic. Well, that's already. I mean, we've already kind of had some sort of minor panics, I think, in the past. And one of the most sort of infamous episodes, at least in astronomy, was back in the 1960s when Jocelyn Bell Burnell was working at Cambridge on her PhD thesis, and she discovered these sort of peculiar types of stars, and the signal that she and her supervisors discovered was so incredibly precisely regular that it was thought, at least briefly, that only an intelligent life form could actually create those signals. Mm-hmm. So they sort of named them sort of semi-jokingly LGMs, little green men. They turned out to be pulsars, sort of type of neutron stars that beams radiation at us and across the universe in a very sort of precise way. Yeah.
And just for the podcast record, when you say intelligent, you are using air quotes.
Yes. Sorry,
so
yes.
Intelligent as defined by humans.
Yeah, again,
right now.
Yes, and this is always a worry, I think, with all of this stuff. Yeah. It's essentially, as you said, it's essentially anthropic. When we are looking for life, when we talk about life, we're essentially talking from our own experience, our own earthbound experience of what we assume life and lifelike organisms actually are. It's very difficult to get into the mindset of something else that might be alive but is essentially fundamentally different to what life on Earth actually is. Yeah. We do try, but we keep being sort of slurped back to this sort of pre-Copernican, I think, sort of way of thinking. Mm-hmm. That whatever's out there is going to be essentially similar to what is on Earth. Yeah. And we have to kind of assume something, because that's, that we have our own intelligence, we have our own way of analysing those signals. Yeah. But of course it could be fundamentally different. It may not be carbon-based. It may not need water.
Yeah, it's the fundamental problem of having the sample of one.
Yes, that's right. Yeah. That's right. Extrapolating from here. Yeah.
I guess one big question is there a chance that there could be, that there could be a signal that we don't even realize is a signal because it's just...
There is a worrying result from information theory, which is essentially the way that signals are produced, the mathematics behind it. And it involves encryption. So if you take a signal and you encrypt it perfectly, it looks like noise. It just looks like the universe just hissing away. So there are some people who say, well, actually, we're being bombarded by alien signals, but their encryption is perfect. And all we're hearing is just static, So that's very difficult to prove from a scientific viewpoint, because you're working with essentially no data. But this is kind of the struggle that we all have when we come to this, is that we're coming up against quite deep philosophical barriers about how we do things, because we're used to having more than one sample. We're used to having more information about what's going on before we formulate the next step of our hypothesis. Yeah. We're used to having a definition of what we're talking about, right? We don't have concrete definitions for what makes something living. We don't have a good definition for what makes a living organism intelligent, quote, quote. We don't have these things to hand. We have working definitions which have varying levels of use. When people do SETI work, they ignore the intelligence question, even though intelligence is the I in SETI. They actually ignore that part and say, well, what I'm searching for is technology. I'm searching for the transmitters. I'm searching for the things that things build to produce the signals that I can see. But they've completely sidestepped the fact of what it is that's done the building. And I think we have a huge issue there, in the sense that we can't concretely point to something and say, this is alive because of these scientific principles, and this is not alive because of the same scientific principles. Because when we try and do that, we find things that are in the wrong category. We end up classifying fire as a living organism, or we misclassify viruses as non-living. And these things tend to happen when we try and have a simple set of parameters. The only one that really works at the minute is that an organism is living if it evolves by natural selection. Now, you could probably construct computer systems that evolve by natural selection. Then what do you do? We've destroyed our last working definition of life.
But don't you think to some degree that having this relatively narrow human-like set of parameters we look for is the best place to start.
Yeah.
I mean, as one thing I think to take away is that what we're saying is we are really sort of scraping the edge of discovering planets. I mean, it's so hard to do. We know very little about the ones we do know anything about. The idea of detecting a signal from somebody else is incredibly difficult as well, even if it's possible. Even if they are sending signals, it's very difficult to detect. So we don't have a large parameter space in which to look for life, I don't think. So putting simplistic assumptions in there is the only room we've got to look in.
And sometimes even if you look at what we have on Earth, that gets puzzling too. Okay, so...
Yeah, on Earth we've got a huge range of species. We can have all those problems, but actually just looking for something which looks like us is the first place to start.
Well, I mean, we're the most technologically destructive, at least, species. But if you think about intelligent species on Earth, usually second place is, not in terms of destructiveness, but intelligence is given to dolphins, right? Mm-hmm. They live underwater. Yeah. So what happens if you have a civilization that doesn't put stuff in their atmosphere?
And that is nomadic and lives underwater and has these complicated social structures as we know them and as we identify intelligence. But
and
we
cannot
never
build
know about
electronics.
them. One of the things, the transmission team was recently interviewing and recording material at the METI conference in Paris. That's messaging for extraterrestrial intelligence. And one of the things that came up was a lecture on the biochemical requirements of life. And basically, they were just talking about what is physically required, what are the physical requirements to produce life as we know it, and therefore the only way we know how to look for it. Which involved, like carbon or potentially silicon structures and some kind of energy and gas exchange, and those requirements are very specific. Like I'm sure you guys can speak potentially a little bit more to this, but it involves rock and moving water and some kind of heat and preferably some kind of variance so that you can push the evolution of an organism past the single cell place.
Yeah, so if you're looking at theories that describe what they call abiogenesis, which is a fancy word for saying making something non-living into something living, there are three components to an organism. There is the data storage part, which in our case data storage is done by DNA. There is the kind of the container, so this is the body, and then there's some kind of energy source. If you can combine those three in a system that interacts and evolves by natural selection, then you've essentially created a living organism. That's in a sense, that's the broadest definition of life. What I find encouraging from a lot of these studies is that when they try and explore different ways of setting up these kinds of systems. So we say, well, I want to set up a system that has these three components, but I don't want to use the kind of standard stuff we have on Earth. I'm going to go to a different part of the periodic table and see if I can make it work without carbon, for example, or I'm going to just take nitrogen completely out of the system and see if this still works. By doing the chemistry in terms of experiments and in terms of the theory of how atoms work, we keep getting drawn back to the current biochemistry we see on Earth. We seem to be one of the most efficient ways in which to build living organisms, in the sense that we're built on carbon chains. We use water as a solvent for chemical reactions. Also, water is everywhere, right? One of the first things we detect, even in the big giant planets that we see around other stars, one of the first things we often find is water. And we also find methane, and we find the other sort of six classic elements that we think are kind of critical to biological systems. So hydrogen, carbon, nitrogen, oxygen, and then phosphorus and sulfur in lesser quantities, but we think they're there. If you have those and you have them arranged in the right setup, it seems to be that you can produce things like what we see here.
Yeah.
But obviously it depends very much on your circumstances and the ratios of each of these things and all sorts of other things.
What I was picking up from this particular lecture in my, artistic non-science background is that even though there are possibilities for life that we may not know how to look for, And this is definitely true the more and more you get into questions of intelligence and interpreting intelligence. But it seems that there are some hard biochemical facts that limit the possibilities of physicalized life, if not. So even if that doesn't define what intelligence means.
There's certainly certain stars we know not to bother to look for. So what sort of timescales does the abiogenesis take?
It depends who you ask.
Fair enough.
So, I mean, if you're wanting to build something intelligent, then you're probably proposing a timescale that takes billions of years.
Yeah.
Because, in most of the history of life on this planet, it has taken such a long time even to get to an organism that's the same size as a human. And that has no bearing on the size of their brain or their ability to do the things that can bootstrap you towards intelligence. So just getting to the point where you have an animal big enough to have a brain that we think is big enough to possess the kind of intelligence that we're looking for, you're talking like 2 or 3 billion years.
All right. So stellar evolution facts. If you look at stars, counterintuitively, bigger stars have shorter lifetimes than smaller stars, and that's just because they burn their fuel at a much higher rate. They have more fuel, but they burn through it very quickly. So our sun will last about 10 billion years. A low-mass star, like Proxima Centauri, will basically last hundreds of billion years, so essentially forever. But then if you move up to higher mass stars, the highest mass stars only live like 1 to 100 million years. And of course, it's only in astronomy where you say things like they only live up to, only 100 million years old. So some of these stars could potentially form planets, I guess, like a mountain.
Yeah,
it's
in
just
theory,
that
they could form planets, but
they're
so
not
some of these are the sort of things I study, which are
Yeah.
a huge beasts which just die way before life could even get settled.
Exactly.
Mm-hmm.
Even if they could form the planet, which is debatable in itself.
So there's no point in looking around bigger stars for habitable life just because there wouldn't be time.
Yeah, so essentially anything that's more than about 2 times the mass of our sun is just not going to have long enough lifetime for life to really form and get started.
Yeah. But then those are the rarer things. The smaller objects, which last for tens of billions of years, there's lots of those. So there's still plenty of planets. I think just touching on what you were saying, Duncan, about the fact that things always seem to point back to us being a good system for doing things. I think we shouldn't be surprised by that in some ways. And again, it touches on whether we should be looking at other types of planets. One thing I think astronomy's been very good at over the years is putting humanity in its place. You're not at the centre of the universe. You are your solar system isn't special. Your planet isn't special. And actually, I wouldn't be surprised that if we did in time find hundreds of other species that actually, statistically speaking, we're most likely to be normal. Yeah. We're hardly unlikely to be a really odd type of species.
That's true.
I don't think there are lots of different species.
Although at least preliminarily from searches for exoplanets, our solar system is not particularly special.
No.
Yeah.
In fact, it's maybe even a little weird. Like, for instance, again, statistics are out because there's some parts of the planetary zoo that we've studied a lot better than others. But one thing that's been surprising is that there are a lot of planets really close to their stars, right? So Mercury in our own solar system has a period of 88 days. And the shorter the period, the closer in it is. We know tons of planets with periods of, 1, 2, 3 days even, very closely packed into their stars.
Yeah.
Yep. So now that we've spent a solid 30 minutes talking about how incredibly unlikely and it is to find life on other planets, intelligent life is even less likely, and how we don't even really know what intelligent means in the first place. Can we venture into, and also how in some ways it's incredibly standard human hubris to even look for, or not necessarily to look for, but to consider the possibility in the first place that as you said, astronomy is really good at putting us in our places in terms of our insignificance. can we ask some weird questions anyway about finding intelligent life and about what that might look like? Because I do think that there is something really important about asking that question. And I do think that there's something really important about speculating